The purpose of this lecture is to extend the linear regression model into a regression model. And to do that, we need to discuss two related concepts, and those are linear in parameters and linear in data. It turns out that there are actually two linear or two linearity concepts in the regression model. So to motivate this discussion of why we need to extend the linear regression model, let's say I have data on labor and capital and total production for n firms, and I want to estimate a Cobb-Douglas production function. So I want to assume that y is some constant c times L to the beta k to the alpha. I have a sample, which I can assume is a random sample, containing total production for n firms, the amount of labor for n firms, and the amount of capital for n firms. And I have three unknown parameters here. And based on my data, I want to estimate these parameters. Well, everything we know about the linear regression model will not help us. If I estimate a linear regression model on this data, I would do something like yi is beta 1 plus beta 2 li plus beta 3 ki plus some error term. And it's clear that these parameters from the linear regression model are not the same as the parameters in the Cobb-Douglas function. We'll see later that we can actually get around this, transforming this model into a linear regression model by logging both sides, but there are cases when you cannot do that. So we need to be able to analyze models that are not linear, models that do not conform to the setup of the linear regression model. Here's another example where we have data on a dependent variable and an explanatory variable. We can find the OLS trend line in Excel by just adding a trend line like this. But it's quite clear from this example that the OLS trend line doesn't do a very good job. The relationship between the x variable and the y variable clearly is not linear. And so a linear regression model will be a pretty bad idea. We'll see that we can actually do non-linear trends. In Excel can also do that by, for example, we can do a quadratic trend. And if we do a quadratic trend, we see that we get a much better fit. So that is something we need to learn about. However, that's not the purpose of this lecture. The purpose of this lecture is to generalize the linear regression model and distinguish between the two different kinds of nonlinearities that might be the case in the regression model. So we have for regression models, we have the linear regression model, which is always formulated like this. No other variations. There's a dependent variable, there's a number of explanatory variables, and the composition is always like this with an added error term at the end. So here is a linear regression model with two explanatory variables. K is equal to 3 in this case, and the LRM always like this, a dependent variable here, an equal sign, a blob here, which is the conditional expectation, and a plus sign and an error term. Now, for now, this is the thing I want you to focus on, this blob thing, the conditional expectation. So what are we allowed to put inside this particular blob? Well, the answer is we can put explanatory variables and we can put the unknown parameters and only the beta ones. Those are the only thing we're allowed to put into that blob, not the error term, not the dependent variable, and nothing else as a matter of fact. As this is a linear regression model, this particular blob is a linear function. So the way to generalize this is simply to allow this blob to contain an arbitrary mix of explanatory variables and unknown parameters. Not necessarily a mix, a linear mix like in this case, but any mix. To make it look as a Cobb-Douglas production function, we may want to create this blog so it looks like xi2 to the beta 2 times xi3 to the beta 3. That's one possibility, but we actually have an endless amount of possibilities here. It's not even necessary for the number of parameters to be one more than the explanatory variables. So what we do to generalize the linear regression model is that we write it like this. We always have to have yi on the left hand side, the dependent variable, and we need an equal sign, and then actually all we need is some blob of these explanatory variables and the parameters. So we do the representation by just writing g, where g is an arbitrary function which will represent this blob, and we say that this function can depend on, we're still going to name that k, that is the number of unknown parameters. So there is a bunch of unknown parameters. There is also a bunch of explanatory variables. We continue the practice of naming the first one xi2 all the way to xi, and let's call it L. Then there are L minus 1 explanatory variables. Then after the blob comes the error term. So here is the linear regression model, and here is the generalization to an arbitrary regression model. Y depends on a bunch of unknown parameters and a bunch of explanatory variables in an arbitrary way, and to that we add an error term. We have L minus 1 explanatory variables from 2 to L, and we have k unknown parameters. And for the nonlinear model, it's not necessary for L to be equal to k. That is, it's not necessary for example, beta 2 to be related to the second explanatory variable. One important issue will still be true in this general model, and that is what happens when the explanatory variables are exogenous. And that's simply because we can take the conditional expectation of both sides. On the left hand side, I will then get expected value of yi conditional on xi. On the right hand side, if we do this conditionally on all the x variables, the g function will be non-random. The parameters are always non-random, and conditionally on x, the x's are non-random as well. And if the explanatory variables are exogenous, then the expected value of the error term is 0. So that's the way to understand this g function, or this blob, the way we talked about it before. It does tell us the conditional expectation of y given the x data. And we have now relaxed the assumption that this function must be linear. So let's talk about this linearity concept a little bit closer, because this g function depends on beta parameters and x variables. And that actually gives rise to two ways that this function can be linear. It can be linear in the betas and it can be linear in the x's. So we say that the model is linear in parameters if this g function is linear in the betas. So if this conditional expectation depends linearly on the betas, then the model is linear in parameters. So here are some examples. The first one is linear in parameters, while the second one is not. So the basic idea here is that g is linear in parameters if I can write this g function as some constant 1 times beta 1 plus some constant 2 times beta 2 plus and so on some constant k times beta k plus potentially another constant as an intercept. The important part being that these constants cannot depend on beta. They can depend on x, but not on beta. Then it's linear in parameters. So that's why this one, the first example, is linear in beta. It has 1 times beta 1 plus a constant times beta 2. We think of the x then as a constant, plus a constant times beta 3. While the second one is not linear in beta. It's not written as a linear combination of the betas. If you're uncertain, then there is a simple way of checking it. You can just take this g function and do the partial derivative of it with respect to any of the beta parameters. So take the first example here. If I differentiate this with respect to beta 2, I'm left with xi2. If this derivative does not depend on beta, then it's linear in parameters. In the second case, I can do the derivative with respect to beta 1, and then I'm left with xi2 raised to beta 2. And that depends on beta, so it cannot be linear in parameters. We can also discuss the linearity of g in terms of the data or the x variables, and then we treat the betas as constants. So we say that it's linear in data if this function is a linear function of the x variables. So the first example, that is linear in data. It's a constant beta 1 plus another constant times xi2, where the second constant is beta 2, plus a third constant times xi3. Here the focus is on the x variables. The second example is not linear in data because of the xi2 square term. Again, if you're uncertain, you can do the derivative test, differentiate with respect to an arbitrary x variable. If the answer contains any x variable, it is not linear in data. If I differentiate the second expression with respect to xi2, I'm left with beta 2 plus 2 times beta 3 times xi2. So it depends on the x data. So we have to be careful distinguishing between these two cases. A model can be linear in data or non-linear in data. It can be linear in parameters or non-linear in parameters. We have 4 different cases. Sometimes you see the expression the model is linear without referring to if we mean in data or in parameters. If we leave that out, then we always mean in parameters, because that's really the important distinction. So when we talk about a linear regression model, then we actually mean a model that is linear in parameters. Now there are a couple of things that you should probably pay attention to. The first thing is that the ordinary least squares method that we've been talking about is restricted to models that are linear in parameters. Only those models can be estimated with OLS. And in this case, it doesn't really matter if it's linear or nonlinear in data, but it has to be linear in parameters. We'll see in the next lecture how you can estimate a model that's linear in parameters but nonlinear in data using OLS. There is actually another method that you can use for models that are nonlinear in parameters. And remembering this O is for ordinary, well, this is also a least squares method, but it's what's called a nonlinear least squares. So it's called NLS. And this can be applied to all types of models, whether it's linear in parameters or not, whether it's linear in data or not. So this works for all regression models. Now, the nonlinear least squares method is very similar to the ordinary least squares. It's based on the same principle, that is to look at the residuals as functions of the estimated parameters b, and then just to minimize RSS. The only problem here is that since these functions will now be non-linear, we will not be able to solve this system analytically, so estimation has to be done using numerical methods. But it's still straightforward to do it if you have an econometrics package. So I'll just give a quick example. Let's say you want to estimate this model. Beta 1, xi2, beta 2, xi3, beta 3 plus epsilon I, where this is the result on the final exam. xi2 is the SAT verbal score, and this is the SAT math score. If you want to estimate this model in, let's say, eViews, here's the data. You can just go to quick estimate equation, and then you just type the equation basically as it's described in, well, right here. But as before, you don't need to add the error term. It's implicitly assumed that it's there. In this case, you have to follow this convention with the equal sign. You can't just list the variables. So you have to do like final equal to, we had a constant, and in eViews that will then be called C of 1. That's my first parameter. Then we have multiplied by SATV raised to, that's the hat symbol, beta 2, translate that into C of 2, multiplied by SATM, and then raised to B of 3. Now I have typed the model just like the way we've specified it. Notice that you don't need to do anything else because the method is set to least squares. So it can do nonlinear least squares, or it can do ordinary least squares. It can actually just see this expression and see that it needs to do nonlinear least squares. I'm not sure if this will work because we don't have that many observations, but we can try. Well, B is not defined. That's a simple mistake. I accidentally used B instead of C. Let's try it again. And it actually did work. you can see that this is a numerical solution. You had to do 30 iterations before being able to find the minimum of RSS. And these are my estimates. So this is my estimate of beta 1, of beta 2, and of beta 3. In Gretel, you can do also non-linear least squares. So you just go to model and you have to specifically pick non-linear least squares here. You need to do a little more work in Gretel. You can type your model like this. That's sort of similar as eViews. Final is some constant times SATV raised to beta 2 times SATM raised to beta 3. And we can use whatever names we want here. Gretel requires you to specify initial guesses for these betas. So you could start initial guesses at 0. Typically, if you can provide the software with initial starting values which are good, then it's typically quicker for the program to find the solution that minimizes RSS. And you need to do one final thing, and that's to specify the parameters. So you would do here just params, betas, and OK. And let's see, we can compare this. See if we got the same thing, 0.05. Yes, it looks like the same result. Notice that the standard errors, the t-value and the p-value, have exactly the same interpretation as in the linear model. So this is the square root of the estimated variance of this guy. This t-value is this divided by that, and we use the t-value to test the null hypothesis, whether beta 3 is 0, and the p-value we can use to immediately check if we want to reject the null or not.